Hello everyone, my name is Yogesh, and today in this episode we shall be extending our discussion of the topics that we have discussed in our earlier episodes, like the Coulomb's law of forces, and we also have discussed the electric field lines, and then the electric flux, and also the continuous charge distribution. Well, perhaps in this episode we shall be dealing with a very fundamental law that was given by Gauss, because Gauss thought that if I can have a relationship between the two charges and the force that they are exerting over each other, then I can also have a relationship between the total flux and the total charge contained in a cubical or even a spherical or some sort of closed shapes. Well, before going straightway to the Gauss law, let us go step by step. The first and very important thing is that we all have some sort of misconception regarding a very important term called flux, and even I had that too, because how do I say that okay, this is the flux or this is the direction of flux? One of the moments that gave me this connection between my day-to-day life and the flux was that when I visited a hair salon. Well, actually what happened there was, when the barber was trying to give me a haircut, he simply held a portion of my hair between his two fingers like this. And so if I consider that I have got only 4 hair and he is holding it like this, then I got an idea. I thought that this is the same way that we are considering the flux. But actually the story is that we all say that if we have got some sort of shape, let it be a square shape, and if we consider the charges and the electric field lines coming out of it, so we will say that is the flux. But actually it is some sort of a deceiving fact, because we have not taken our area of interest. Just like the barber, he is there to give me some sort of haircut, but he will do it step by step. First he will choose a particular area of his interest and he will select a particular quantity of my hair to be cut down. This is the same thing as we do, that is we have some sort of say a spherical shape or a square shape. We simply take some of the electric field lines by considering that okay, this particular portion is our area of interest, and then we take that much amount of electric field lines coming out of that particular area or volume, and that gives us the flux. So this is all about the story of flux, how to take that. The very next thing is that how to take the direction of it, because if I have got some square shape, so there are so many areas where I can get it. Say suppose you are playing Ludo and you have that Ludo cube, you simply roll it. So you can simply say that if the upper face that you take while playing gives you 6, so that means you have got 6 lines of forces, or if you get 1, then you have got only 1 electric field lines of forces. This is a very similar example, because you do not consider what's there on your right or on your left, or what is there just behind it, but you only consider the face that is on the top. This is the same way that we will have to consider the direction of electric flux, because even if I consider a simple planar sheet, there could be 2 directions of flux, one is upwards and one is downwards. But just like our Ludo cube, we only consider the upper face, and that's why we play Ludo like that. And I think maybe in some way electrostatics also plays with the electric field lines. So this was what we have discussed about the electric flux and how to take the direction of electric flux and all those things. Also we note that there are some charges, and whenever a charge resides inside a body, so there could be 2 cases. One case could be that we have some discrete charges. I have got, say suppose, one Ludo cube and I have got 4 q charges into it. The other one which has got, say suppose, minus 2 q charges into it. But in our later episodes, we have also discussed that this could not be the same case everywhere. Means I cannot simply pick up a discrete charge and say that okay, this is the thing I want to go for, or this is the thing I want to ponder over it, or I want to take into consideration. So that gave us a new direction of looking into charges, that was the continuous charge Wood distribution. So Gauss said that I have got so many concepts. I have got the concept of electric flux, the direction of electric flux, and I also have the charges contained in a body as a whole. Please remember, Gauss law is all about the charges contained in a body in a continuous form, not in a discrete form. Well, now since we have got all the essential elements to have this new dish, we shall now be going for the mathematical interpretation of this very beautiful yet easy law. I know that you must be thinking that, oh, this is a Gauss law, it deals with some flux and it deals with the total charge that is there in some closed shape like a cube, like a sphere, like some you say a paralleloid, anything you want. Then you must be thinking that it is a bit hard. Well, the reality is that it is as easy as simple ABCD. Yeah, that is. Okay, so you don't agree with me, I will make you happy right now. Say suppose if I consider a sphere, and since I am interested in taking out whatever is the relationship between the electric field and the flux and the total charge contained in it, what I will do is I will simply take a portion of that sphere. It is just like if you have got an apple and if your mom says that okay, cut this apple for us. So what you will do is you will simply cut into some pieces. So you simply take out a piece of it, have a look at it like this, and then you will simply say, okay, I am considering a very small circular portion over it, and you simply say, okay, some of the electric field lines are coming out of it. So in this way, what you got was, you got a particular portion of your interest from which you will find the electric flux. And now we go back to our basic laws, that is how to find out the electric field. So what is the formula of electric field, means how will you find out the electric field? Oh, I think I missed a thing. Yeah, okay, I will say that the total charge contained in that particular your area of interest is say suppose small q. Now we have to do it. Yes, exactly, that is E equal to 1 by 4 pi epsilon naught times the charge contained, that is q, upon r square. Is it all right? Oh, thanks for correcting me. I just forgot to mention the direction vector, that is r cap. Now this is a very simple thing. Say suppose it is your equation number 1, and now I will go for the particular element that I am considering, that is my areal element, my area of interest. So when I go for it, I will simply say if it is say delta S. So if it is a sphere, then we must have something like that your 4 pi epsilon naught square, or if it is a square, or if it is a cube, whatever it is, you simply have to put the area of that particular interestial area that you have taken. That is even if it is a square, that is side into side, or if it is a volume, that is length into length into length. That depends upon you, how you are cutting that particular shape of an apple. So once you find out that delta S, now you are free to go for the flux. Okay, what is flux? Yeah, it is phi equal to E dot ds with some direction vector. That is really very important. But since you included that direction vector in the electric field, so you are free to go. Now you will encounter a very simple thing. Once you solve that whole equation, that is phi equal to E dot ds, with E is your 1 by 4 pi epsilon naught times the total charge contained, that is q, divided by r square, and the direction vector r cap, and you multiply it with the area of that particular portion that you have taken in consideration, you will find that you only have two terms. That is, since I have taken the sphere, so what I will get is, that is 4 pi r square delta s. So once I put it there, I will find that phi is equal to q by epsilon naught. Are there some bells ringing in your mind? Yes, that is the beauty of Gauss law. Gauss law simply states that the total electric flux coming out or the total electric flux leaving, that is a better definition, our particular area of interest is nothing but the total charge contained in that area times the epsilon naught term. Well, after this I leave everything up to you. Means since you have got the apple and you have found the Gauss law from it, you can either eat it or you can even keep it forever. But what you got was that you got the taste of Gauss law. Now, since we have done this, we must also mention some of the important steps that one must follow while working out on Gauss law for various shapes. We must take into consideration some of very important steps that we must keep in our mind while we are simply going down the lane and trying to derive or trying to find out the flux and the charge relationship, no matter whatever the shape of that particular area is. So the very important instructions for the Gauss law is that the first one is that Gauss law is valid for all the shapes that are present in the whole universe. Means I am not saying that anything that is around you, that is everything in the universe. If I can get that much power or that much will to go for the sun, I can even find out the concerned quantity out of it, or anything from even an electron to everything you can find out. But a very important thing is that you have to consider some area of your interest. For example, in the case of an apple, when you cut it into pieces, you simply took some part of it. Do you know what do we call it in terms of some scientific language, or what Gauss said? It is known as the Gaussian surface. Actually, because what I told you in the previous lectures was that since we want to find out the total electric flux, and if I am not interested in going for the continuous charge distribution, what I will do is that I will simply take some area where I can say that this much charge is present, and then I will find out the electric field, the corresponding electric flux, and then I will integrate it all over the area. As simple as it is. But when you are considering that particular portion which will give you the electric field, or if you proceed further, the electric flux with respect to the charge that you have considered or your area that you have in your mind, so that particular area is known as the Gaussian surface. You can just imagine if you can have an orange, and if you can there are some orange peelers out there, means they will peel up the orange, and then you have got some juice material, that is if you go for any normal grocery shop, they will give you some sort of instrument that you can simply put over an orange, and you will simply insert it like this. It is some sort of a cylinder, and when you push it, it will simply go into the orange and the juice will come out. That is, you can simply pour it like this. Or it could be any example, like if in our household we all make laddus. That is a very tasty example. So if a mother wants to have some nuts into it or some almonds into it, what she will do is she will make them, and then she will take some almonds or something like that, then she will insert it. Actually our mother's thumb that she is inserting there, we can take that, so when she will take it out, you can see that there is some sort of gap there that is made in that particular laddu or that particular sweet. That particular gap is nothing but an imaginary Gaussian surface. So whenever you have got some body, you simply take into account that okay, this is some sort of an imaginary cylindrical section that I am taking into consideration, which will include the charge that I want to take with me, and then I will find out the electric field and the electric flux corresponding to that charge. So that surface is called the Gaussian surface, and it is really very important because there are so many bodies in the whole universe, and we can only find out the symmetrical aspects. So by using this Gaussian surface, we can find out the electric flux linked to it by having that particular sort of symmetry that is needed. This is what we all have discussed today. We went straightway through the definition of electric flux, a very common life example. Then we discussed the Gauss law, how Gauss arrived at it, and then we also would discuss some of very important features of Gauss law, that is the Gaussian surface and the symmetry of the objects. Thank you.